this guy who I forgot his name is Sean Parrot is a C++ joke for those of you that either listen to ADSP or know who Sean Parrot is. Um, it was initially pink, but then I got a request from Bryce to change it to green because it matches the NVIDIA colors more. So, anyways, there's been some good feedback. A number of stars showing a moderate amount of interest for a research library, which is great. And that brings us to the meaty section of this talk. So we're going to go over 4 different problems in this talk. Some of them we're going to show the C++ and Thrust solutions for. Some of them we're just going to show the Parrot code for. And this is to give you an idea of what this library looks like solving some simple problems in C++ versus what it would look like in Thrust versus what it would look like in Parrot. And ideally, the Parrot code is going to be the simplest code at the end of the day. So the first problem is the sum of squares, which is basically you want to generate a sequence of numbers up to a given number n. You want to square those numbers, and then you want to sum those numbers. So this is a common computation, and the reason I'm including it as the first one is it's a very simple problem. This isn't a complicated problem, so hopefully you'll be able to think about in your head, how would you solve this in C++? So, start to do that now because I'm about to show the solution. And then how would you solve it to target a GPU in a library like Thrust, and then what's the equivalent in Parrot? So without further ado, there's a number of ways that you could solve this in C++, but we are going to make use of the ranges library. And if you're going to use the ranges library, it might look something like this in C++ 23. So we have an iota view in order to generate our sequence from 0 to n. And then we've got our transform view, which is going to do our square operation. So we're passing a lambda that's multiplying just the value by itself, aka a square. And then unfortunately, we don't have an algorithm that we can pipe in this pipeline. So we need to pass the composition of the iota view and the transform view as the first argument to an algorithm that showed up in C++ 23 called ranges fold left. So this is similar to accumulate with a couple differences. And the nice thing is, though, is that you can pass this view as an argument. You don't need to get the iterators from it, and it'll just work. So we want to do summation. So the binary operation that we are sending with fold left is the stud plus. And that's it. So 3 different algorithms, fold left, iota, and transform. A little bit of noise in terms of the namespaces, stud : ranges : views : so you might want to use some aliases in order to shorten that up, but just one way to solve this problem. And so this is hopefully at this point you understand at a bare minimum what this problem is. So how would you, if you want to parallelize this and run this on the GPU, how would you solve this in a library like Thrust? So Thrust, if you're not familiar, is inspired by the standard template libraries. So it has a lot of the same algorithms and some extras that exist in the algorithm header. And it has some extra features called fancy iterators. But hopefully you will recognize, some of the, syntax, if not under a different namespace for these algorithms. So here we have a function object on the first line called square. And this was, I believe at the time, this was back in September when I generated this code. I was using Claude 3.7. And I asked Claude, based on the C++, can you generate me Thrust? And this is what it gave me. So this is not exactly how I would code it. I wouldn't use a function object. We'll clean this up in a second. But at least it's doing the correct thing. We're generating or creating a device vector called dvec. Then we're using an algorithm called sequence, which is an algorithm equivalent of the iota view that was in C++ 20. And then we're making use of an algorithm called transform reduce. So we're combining our transform view that we had in C++ with the fold left into a single algorithm that is called transform reduce. So this actually exists in C++ 17 as a parallel algorithm. So you can find it in the standard namespace std : transform reduce. And this enables you to pass a binary operation and a unary operation. So the unary operation here is the square, which we're getting from our function object. And then the binary operation is the plus, which is exactly what we had in the fold left solution. So This is nice that it works, but there's a lot of issues. So if I were to write this myself and not get AI to generate it, I would avoid this function object. So if you're using the NVCC compiler, there's a flag called extended dash lambda that enables you to use lambdas with algorithms now. So at a certain point in time, before I was using Thrust and the MVCC compiler, you couldn't use lambdas with algorithms. And I guess for that matter, before C++11, there weren't even lambdas. And I think Thrust actually, the genesis of Thrust, post dates when C++11 came out. But the point being is, at some point, you couldn't use lambdas with algorithms, which is why there's a lot of code out there that's using function objects instead of lambdas. Now, however, you can use lambdas. You just have to pass the dash dash extended lambda flag to MVCC. And this is my preferred version. However, there is still a glaring kind of design flaw. This code does work, but there is something that is unsatisfactory about this. Maybe I'll wait 3 to 5 seconds if anybody wants to see if they can identify. Either you can post it in the chat. What's wrong with this code solution? What's suboptimal about it? But I'm only going to wait a few seconds if there's no takers. I don't see anyone typing, although I'm not sure if Discord gives you a preview if there's multiple. There is someone. Uzo is typing. We'll wait for Uzo's response. They could be copying between devices. Kind of. You're halfway there. Technically, we're creating a device vector, which is going to live on the GPU. So there's not actually a copy between the host and the device, but you're in the right direction. And that's that we are doing this allocation for a device vector where we didn't in the C++20 or 23 solution. We didn't have to do an allocation. We started from views, which are essentially lazy mechanisms. So you have a lazy IOTA or index generator, and then you have a lazy transform, and then all of that just feeds directly into a reduction. So you don't need to allocate any memory. Whereas in this example, we're allocating a device vector, materializing our IOTA sequence using the thrust sequence algorithm, and then we're calling a reduction in the form of transform reduce. So we have an allocation here which is unnecessary, which is kind of proven by the fact that in the C++ solution we didn't have that. And so the way to get around this is to not reach for the algorithm sequence. It's to reach for the iterator, the fancy iterator, counting iterator. So counting iterator is morally the same thing as the IOTA view in C++20. This gives you a lazy mechanism for basically building this sequence of 0 to n. And then you can pass this to your algorithm transform reduce and avoid that allocation. So whenever you can, you want to avoid kernels, and whenever you can, you want to avoid allocating because it reduces your memory footprint and it's just going to be faster at the end of the day. And so this is the ideal solution, in my opinion, using a counting iterator, which isn't going to allocate anything, and then making use of a transform reduce. However, now that we have made it through a couple different thrust solutions and we're at the ideal solution, we have the problem that there's a couple different ways to spell this, which is what is confusing about the Thrust library. Thrust is a very, very powerful library. The problem is I don't want to have to think about, should I reach for sequence or should I reach for a counting iterator? When should I reach for an algorithm versus when should I reach for a fancy iterator? And here, you can spell this a couple different ways. Note that we were calling the transform reduce algorithm before, but now we're calling another fancy iterator and wrapping the counting iterator inside that. So we're making use of two different iterators now, fancy iterators, counting iterator and transform iterator. And the transform iterator is the moral equivalent of the transform view from C++20. So this is effectively the exact same thing. We're just using two fancy iterators and the reduce algorithm versus using one fancy iterator and the transform reduce algorithm. And so we've got these two different solutions. It's not great. Which one should we use? Which one's better? I don't want to have to think about this. So this is where Parrot comes in. So we've seen the C++ solution, we've seen the thrust solution, and now this is a step-by-step solving of this problem in Parrot. So we've got our sum of squares, takes an integer, the first thing we're going to do is we're going to create a range. So we've seen now 3 different names for this algorithm. We had iota in C++20 as a view, we had sequence in Thrust as an algorithm, and we had counting iterator as a fancy iterator in Thrust. And now we're calling this range in Parrot. I think that's because range is actually the best name for this algorithm. And if you look at across languages, Python, most languages call this range. So this is our equivalent of iota. Then we can call a function called square, or sq, short for square, and then we can call sum. That's it. We're done. We've got no, fancy iterators. We've got no algorithms. Everything is just a method on a fusion array behind the scenes. And so you start with a range or an array or a matrix, and then you just chain these methods. And this is equivalent to the Thrust code in the last 2 examples that you saw. So even though that this is much simpler, performance-wise, it's identical to the hand-rolled Thrust code using the fancy iterators, or whether that was the reduce or the transform reduce, which is really nice. On top of this, we have the ability to print out the result and also the intermediate steps if you want. So a big complaint about libraries like ranges in C++ and iterators in Rust is that you can't really debug these, because how do you print out the intermediate step of these expressions? And I've built that into Parrot. So you can build these things up incrementally, or if you have some issue, you can just inject a print at any point in this method chain and see what the result is. And if we want to be fair, because on the previous slides we were showing the printing and the included headers, this would be the full code for Parrot. So the goal that I'm trying to drive home here is that this is super simple in terms of programming with it, but also in terms of how you think about using this library. You don't have to spend as much effort trying to decide, when do I reach for fancy iterator, when do I reach for an algorithm, or even if you're in C++, when do I reach for a view, when do I reach for an algorithm? Here, it's all the same thing, and we've hidden the complexity behind the API so that you can just choose for the right method and expect that the right thing will be done behind the scenes. So I'll pause here. Are there any questions? Because I've covered a lot already, and we're about halfway through the content. If I don't see any typing, we'll just keep motoring along, but we'll pause for questions. And if there aren't any, we'll keep going. I see no typing, so we'll continue. But like I said, if at any point folks have questions, just feel free to interrupt. So the Parrot API, this is a high-level overview of everything that is offered in the library at this moment in time. So you might remember from the sidebar of the docs that there were different categories of operations. So there's a lot on this slide. The goal is not for you to read everything and understand the API from start to end. The goal is to take away a couple different things. The first one is the categories. So you can see in the first 3 columns, there are pink titles for the 3 different categories. There's fused, conditionally fused, and materializing. And the takeaway here is that anything that's in the fused category is going to avoid launching a kernel. You don't launch a kernel on the GPU until you have basically called an operation in the materializing category. So you can chain as many of these as you want, back to back to back to back, and technically it's just going to be a lazy operation. And then when you do a reduction or a scan at the end of the day, or a sort, then it'll materialize, and you can still interchange these things. You can do some lazy operations, then a materializing one, then some more lazy ones, then 2 materializing back to back. Everything just works. But the idea is that the longer you can stay in fused land, the fewer kernels you're going to have generated for you. The second thing that I want to point out is that inside of the major categories, there are the minor categories. And at the top of these sections, for some of them, there's a starred method. And what that typically means is that every method below the starred method is just a specialization of that starred method. So map is the equivalent of transform, the unary transform in C++, that is basically an algorithm that just takes a unary operation. So anything that's a unary operation in Parrot is going to be found in this category. And so, if you want to get the sign of your integers, or if you want to square a number or square root a number, you can just do these. And these are all implemented in terms of map. Same thing for one index maps. Or actually, this should say, or this is a one index map with a binary operation. So addition, subtraction, etc. These are all found here. And then we've got map adjacent. So map adjacent, if you're familiar with these C++ algorithms, is equivalent to, in C++ 98, it was called adjacent difference, but in C++ 23, we got adjacent transform, which is the better, more generic version of it. And it's a algorithm or a view that takes a sequence, looks at adjacent elements, and applies a binary operation to each of those adjacent elements. So the two specializations here are deltas and differ. So the binary operation for deltas is subtraction. It's taking the difference between adjacent elements. And differ, the binary operation is not equal to. These are quite useful, especially in finance, which is where they're borrowed from a language called Q. And then for the other ones that are implemented, keep is basically a compaction. So if you're familiar with filters, keep is a compaction that works with a Boolean mask. So if you've given an array and a Boolean mask, it'll keep the ones that correspond to true. But note that this is conditionally fused. So if you're not actually needing that materialized compaction at the end of the day, for instance, we're going to see an example later where you're counting the number of unique values using this C++ definition of unique. That doesn't need to be materialized, so that can be fused. And we'll talk about that a little bit later. And then we've got reduce and scan. Everything below the reduce is a specialized reduction, all, any, max, min. And the scan also has specializations which are preceded by S, so alls, maxes, mins, etc. I think the next slide is highlighting the rank polymorphism that exists in this library. So for the one index maps, both the unary and the binary, these work rank polymorphically, which is two really big words, but it's actually quite simple. And before we talk about that, this is where I'll address, what is functional versus array. Originally this talk was called functional GPU programming. Then I've kind of renamed it to array GPU programming. In my opinion, array programming, and this is with, kind of quotations because a lot of people would take issue with this, but my mental model for array programming is functional programming plus rank polymorphism. So, and if you want to, talk about the languages that I'm a huge fan of, Iversonian array languages like APL, BQN are kind of like functional languages plus rank polymorphism plus symbols. And BQN is the most functional of these languages. Technically, APL and WeWa, they're missing a few things to really make them functional languages, but BQN has everything you need. So if you want to put this in a diagram, functional is your outer circle. Then a subset of that are array languages that have support for rank polymorphism. And then inside that, if you've got a symbolic language like APL, then you have an Iversonian array language. So this is a slide that I've shown in a couple talks that just highlights the differences between different array languages. So in the middle, you've got your Iversonian ones, which is the green and the red that we saw in the last diagram. And there's a GitHub repository called Array Language Comparisons if you're interested in this graphic and checking out these languages. So back to rank polymorphism, though. So if you want to add, for instance, a scalar to a matrix, how would you do that in C++? So this is the easiest. You just create a nested for loop where your outer for loop is looping through each row in your matrix, and then your inner for loop is looping over each element in your row. And then once you have access to every element via reference, you can just do +1. This is a lot of code, in my opinion, and not great. You can try and do this with ranges, but it's even worse, in my opinion, because you're nesting the transform views, and then you have to use a lambda, so it's just incredibly messy. However, if you have rank polymorphism, this is what you have to do. So basically, rank polymorphism is just a fancy word for saying that you can apply unary operations and binary operations that fit into a certain category of scalar operations like addition or square rooting or squaring. And regardless of the shape of your array, whether it's a vector and it only has one dimension, or it's a matrix and it has two dimensions, or you have some arbitrarily ranked array that's got multiple dimensions, that's greater than two, if you're trying to add a scalar to this, it just automatically works. Like if we go back 2 slides, what we were trying to do here, like this is incredibly simple, right? You have a matrix and you're just trying to add a scalar value to every element in that matrix. Conceptually, it's very easy. But the way that you have to basically bend over backwards in order to do this by nesting 2 different for loops and, naming your row and then naming your element, it's all very, very unnecessary, which is kind of the idea behind array languages, is it makes operations like this super simple. So whenever you have a binary or unary operation in those kind of one index categories, you can do, something super simple like this. So we also have a method called add if you want to do it that way. I obviously prefer the binary operation. And so all of these methods that you see on your screen are rank polymorphic. So whether you have a scalar value, rank 1 value, rank 2 value, or an arbitrarily ranked array, you can use these on that, and it's just going to work for free, which is fantastic. And so this, I believe, is just showing the overview of the API one more time. And I think I added this. So this wasn't in the original talk. There is another library that I'm currently working on at work, which is a Python version of this Parrot library. And this is a kind of comparison of how each of these operations is implemented. So you can see here that anytime you see the parrot emoji, it means that this operation is implemented in terms of another already defined parrot operation. So a lot of this is actually just implementing a few fundamental algorithms like the map, map2, and keep, and then all the other operations are implemented in terms of those, which is quite nice. And hopefully I'll be releasing this as a paper at some point in time. Moving on to the second problem. So I believe that's the second of 4. And this is taken from an open source library called Paddle Paddle. If my memory serves correct, the Paddle stands for Parallel Deep Learning Framework, kind of, something like that. PA, the DL, and then they added the E. And let's see, is it going to go to the next? This is why I restarted my computer, because the animation that it's trying to do, it freezes the browser because it's so involved half the time. And it's, here, we're going to skip out. Yeah, see how slow it is. All right, well, we'll see if this works. So this is, and I've actually already simplified it. Oh, there we go. So this was the initial code. And you can see that at the top, I have excluded the full name of this function. And so a part of this is to see if anybody can figure out what this code is doing. Obviously, it is too complicated at the moment. So we are going to simplify this and then see at the end if anybody can figure out what this code is doing. So first things first, we can remove all of the parameters and a lot of the initialization code because it's not important to what this algorithm is actually doing at the end of the day. And so now we have a for loop that is going from I equals 0 to the number of rows. So basically it's doing a row-wise computation of something. So what is that something? So the first thing that we're going to isolate, if this animation works, is the following piece of code. So let's zoom in a bit, and it's a call to inner product, and then it is doing something. And the question is anybody able to figure out what this inner product is doing? And a hint is that if you're not familiar with the inner product algorithm in Thrust, it also exists in C++. And it's a variant, or basically a differently named version of transform reduce. So we have 2 different binary operations here. One of them is plus, and one of them is not equal to. So a hint, if you're not familiar with this, is the plus is what is corresponding to the reduce in the transform reduce, and the not equal to is a binary operation that's being applied as a transformation before we do this reduction. Any thoughts on what this is doing? I see no typing, so I will give the answer away. And it is computing, or use those typing again. So we'll take a small A small break wall. While we're
Never
waiting
mind,
for
never
that,
mind. I'm typing.
I will uh, I will get a drink.
You can go on. I have no idea right now.
Okay. So this code is computing the unique values, the count of the unique values in a sequence that is defined by begin and end. And so what you can try to make out is that these first three arguments are iterators that are defining two different sequences. So the first sequence is begin to the second last element. And the second sequence starts from the second element, the +1, and then goes to the end. So this is a twisted way of looking at adjacent elements because your first sequence is 0 to n minus 1, and then your second sequence is from 1 to n. And so it's then applying a binary operation not equal to those adjacent elements. And so now you have a basically map or a transformation of all of the times that adjacent elements are not equal to each other. And so what does that mean? It means that anytime you have an adjacent pair of elements that aren't equal to each other, that if you're scanning through the list of values, that's when a value changed. And so the number of changes that you have in a sequence of numbers is one less, which is why we have a 1 plus here, than the number of unique values. And note that this is unique values as C++ defines the algorithm unique. So there's unique in general, which just means what are the unique values regardless of order. But C++ unique says unique is the number of unique values that are not equal to their neighbors. So you can still have the same value twice as long as it shows up somewhere else in the array. So this is a very, very convoluted way of counting how many unique values do you have in your sequence, which, you could use, adjacent transform if we were in C++. But funnily, in Thrust, there's actually an algorithm called unique count. So all of that code that was passing two different sequences using the +1 and -1 on iterators and then passing two different binary operations to an inner product, all can be simplified to this single line of code, which is very nice. When I saw this, I was like, why isn't that person using unique count? And potentially it's because when they wrote the code initially, unique count wasn't there. Or maybe they just didn't know about the existence of this algorithm because unique count doesn't exist in the C++ STL. So we're going to go on a little mini digression about the implementation of this. So we just saw this implementation, 1 plus inner product, first to last -1, and then the second range starting at first +1, and then two binary operations, plus for the reduction and not equal to for the binary transformation. However, you could, similar to how we saw earlier with Thrust, there's always a couple different ways to implement this in Thrust. An alternative is the following. So we've got a fancy iterator that you haven't seen yet called zip iterator. And this is for bundling two different sequences together. So instead of passing two different sequences to inner product, which takes two different sequences, we could just bundle the two different sequences into a single iterator, pass that to a transform iterator, and then if we bundle the binary operation not equal to in this function called makeZip function, we now have the ability to just pass this basically iterator, which we're calling map, to our reduce algorithm and call plus for our binary operation. So we still have the two binary operations not equal to and plus, but we are making use of reduce now. And I kind of like this implementation better because it obfuscates less what this code is actually meant to do. When you see the inner product in the last slide, it's very unclear the kind of idiom and the pattern that is being used there in order to count the unique values. Whereas here, I still wouldn't say it's completely obvious because you still have to make sense of the not equal to and the thrust plus. But the fact that we're using a zip iterator and you can tell that we're zipping, the first element in the sequence and the second element, it makes it a lot more clear that at least we're looking at adjacent elements here. What we're doing from there, we still have to figure out. But I like this code better. And if you actually go and look at, like I said, Thrust has an algorithm called unique count, and Thrust is an open source library. If you go and look at the implementation of Thrust, this is a bit simplified, but it's essentially, morally the same thing minus a few details. This is the implementation in the Thrust library. It's making use of the zip iterator. It's doing the pattern that I showed a little bit different. Instead of calling the make zip function, it's calling make tuple. And then it's using a hand rolled zip adjacent not predicate, which is very confusing. But it's a hand rolled thing instead of using the zip function and the not equal to. But effectively, this is the same thing. And when I looked this up, I was like, oh, that's right. There's a count if in Thrust. There's not really a count if in array languages, so it's why I always forget about this. And so I took this and I was like, well, technically, you can go back to my old solution that I just showed, and you can replace that reduce with a count if. And now you have an even nicer solution, in my opinion, making use of a zip iterator, the zip function, and a count if, which, like I said, this is still not completely obvious what this is doing, but it's much, much nicer than the inner product. And so we're in the middle of a digression. The point being here is that we've now looked at 1, 2, 3, technically 3.5, if you count this as different from the Thrust official implementation, ways to solve this in Thrust. How would you solve this in Parrot? So this is beautiful, in my opinion. We're making call to map adjacent, which is the equivalent of, adjacent transform in C++23. We're passing the not equal to binary operation. We're summing, and then we're adding 1. And if you remember from the specializations of map adjacent, we actually have a specialization for map adjacent when your binary operation is not equal to. It is differ. So this is how you would implement unique count using Parrot, which is so much nicer. Technically, you could argue that there's the two different ways to implement this if you use map adjacent instead of the specialization differ. But really, I would say, you should know not to reach for map adjacent when the specialization is there. So there's really just one way to implement this, and it's super, super nice, in my opinion, compared to the 4 solutions that we saw in Thrust. This is a single line. It's a call to 2 different methods, and it's so much clearer what's doing here. If I were to ask you what is this code doing and I didn't have unique count here, it's so much easier to understand that we're counting, the unique values as C++ defines unique compared to those other solutions. So part of the pitch for Parrot is you end up writing code like this versus what you saw in Thrust. And in general, this kind of scales. So there's a number of algorithms in Thrust that are hand rolled specifically because juggling these iterators and algorithms, it has some cognitive overhead. So, we just looked at unique count, which is a zip iterator plus count if, but transform reduce we saw earlier is the transform iterator plus reduce. And we haven't talked about this algorithm tabulate, but tabulate is basically a counting iterator plus transform. In Parrot, whenever you're reaching for these kinds of patterns, you don't even need to think about it. You just basically combine the methods that you need in order to spell it. And, the fact that one of these is the equivalent of an iterator behind the scenes, you don't have to think about, which is fantastic. You just get the same, performance with a much simpler API. That's the end of this digression, and it brings us back to trying to decipher this code. So you can see now we've replaced our inner product with this unique count. And if we rearrange this code, let the animation take 10 seconds. Oh, you gotta love PowerPoint in the browser. That's what you get for using a Linux operating system and not having access to the PowerPoint application. If we reorganize this now compared to where we started, this is a lot easier to try and understand what's happening now. So we've got our thrust sequence, which we've already seen. So this is for generating, an IOTA sequence. And we're storing this in the indices data. And then we're making a call to an algorithm called sort by key. So sort by key is an algorithm that is a little bit confusing. It is not doing what you might expect. So when I first saw sort by key algorithms typically mean one of two things. In one sense, it can mean that a key is a unary operation that you are using to kind of, if you're familiar with projections in C++20, you basically are applying a transformation and then doing some kind of operation after you've applied that transformation. So say you wanted to get a string, you had a list of strings and you wanted to get the longest string. So you're doing a maximum reduction, but you're doing a reduction, but you're not actually looking at the strings directly. You're looking at a property of the string, which is its length, or the dot size method. So you could use a dot size projection in order to find the string that has the longest length. That's one of them. Another one is basically doing the same thing, but for binary operations. So when I see sort by key, I think it's trying to sort something, but also by like a unary operation. So if you want to sort that list of strings by its length, you have to pass a binary operation or a unary operation size, and then it's going to apply the sizes each time it's doing a comparison. That is not what sort by key does here. Sort by key takes two different lists. So begin and end defines one range, and then indices data.begin defines a second range. And it sorts both of the ranges by the first range, if that makes sense. So this would be the equivalent if you were pairing the two sequences in a vector of pairs or two tuples, and then you were sorting that vector based on the pairs is essentially what's happening here. So it's going to be driven by the first value in that pair. So a little bit confusing. We're sorting both begin and end and indices, and the sort pattern is going to be based on the first series. Then we're doing the unique count, and straight after the unique count, we're doing a reduce by key. So this is where the by key actually kind of makes sense. A reduce by key is what's known as a segmented algorithm. It takes a binary operation, determines where there is a failure for that binary operation, so a predicate function that is returning false, and then those breaks define the segments, and then you're doing a reduction based on those segments. So unique count, what it's doing here is it's determining how many segments are we going to end up with for our reduce by key, because we need to allocate some memory in order to store the result of those reductions. And so the reduce by key, a little bit confusingly, is summing the constant iterator 1 over the keys. And what that means is it is basically counting how many of the unique values in our sequence are there, if that makes sense. And then after it does that, it does a maximum on the counts that have been computed from our reduce by key, and then ultimately returns that with the index at where the value of that maximum lived. So ultimately, this is finding the value that occurs most frequently in our data, which is known as mode. And so, mode is a statistical, measure, but it's also known as like most frequent value. And how would you solve this in Parrot? So this is kind of cheating because, I just added a stats mode. But if you look at the implementation of mode, this is the equivalent of what we just saw in the unique count, the sort by key, the reduce by key, and the maximum. So for each row in our matrix, we're doing a sort, a run length encode, which is basically going to encode the length of all of the runs of values, finding the maximum from those lengths using the max by key, and then just taking the value. And in order to get the index, that it was doing at the end. We just do last index of, and you're done. So all of that code that we started with can be boiled down basically to this if you're using Parrot, which is pretty nice in my opinion. All right, so that brings us to our second last example, and these ones are a little bit shorter, so it probably won't take anywhere near as long as the first two. So this is an example that I've talked about in a couple different conferences. So you might have seen this before. The problem is sushi for two. You're given two different types of sushi, which in the problem are represented by the values 1 and 2. And the goal is to identify a subsequence from this list that has only, one run of the blue fish and one run of the brown fish, and they have to be partitioned one after another, and they have to have the same number. So that was poorly explained, but in this example, the maximum run meeting all these criteria is the 4 fish at the end. So you can see here that we've got both 2 brown and 2 blue fish, and they're partitioned. So they're not switching blue, brown, blue, brown. So the goal of the problem is find the number, the maximum number of fish that fit this pattern. It doesn't necessarily need to go blue and then brown. It could go brown and then blue. But it's, it has to have the same number of blue fish, the same number of brown fish. It has to be partitioned, and it has to be contiguous. So if we look at a different example, does anybody know what the result would be for this test case? I see one person unmuted.
Thinking it should be from fish number 2, then the set of 3, and then the set of 3 brown fish. So the 3, 3.
Correct. Yes. And Uzo might be typing the same thing. So this is the answer for this question would be 6, because you're taking, 3 blue fish, then 3 brown fish, and this meets all our criteria. So this is a toy problem that I solved, I think it was back in 2018 or 19, and it was in a Code Forces code competition, if any of you know of Code Forces. It's similar to LeetCode, but was targeted more at people that were into competitive coding. And I specifically remember I solved it in Haskell because I knew I could solve it really simply in Haskell, and that solving it in C++ would have been such a headache. And this was before ranges existed. So, in another talk I mentioned, I solved this and I showed what it would look like in C++ before ranges. And if you want, you can go check this talk out later. I gave it back in 2002, 2023. I can't remember. It was shortly after the pandemic, I believe, ended. And this is the code that I showed you would have to write. And you might be able to do this in a couple lines less. And I remember actually I made it got posted on YouTube, and then someone posted in the comments like, "Oh, you could actually do it much easier." But the solution that they had done violated what I was trying to do here, and I was trying to solve this without allocating any memory for vectors. Because if you think about this problem, all we're doing at the end of the day is counting and summing something up. Our answer is a single number. And so you shouldn't have to materialize anything in a serial solution. You might have to on the GPU, but sequentially, you should be able to do this. But the problem is that you have to keep track of so much stuff. You have to keep track of what's the current sushi type that I'm on, how many in a row have I seen, how many were previously in a row of the different type of sushi, and then a couple other pieces of data. And so it's just very, very cumbersome. And so you don't want to have to solve this by hand rolling stuff. And so in that talk, I showed that the closest that we could get in C++ today, with C++ 23, was the following: making use of a bunch of concats, filters, zips, zip width. Kind of nicer, kind of not. And there is an alternative solution that uses a chunk by that's actually only a couple lines that I probably should have shown here. But the point being is that this is not great. And in Parrot, you can now solve this in very nice fashion. So this not only is basically just method chaining, but it is GPU accelerated. And there are only two spots where kernels are being launched. So the where is a compaction, and the max R is a reduction at the end of the day. Every other operation that you see here is lazy. So the differ is basically a map behind the scenes, and then map adjacent is also a map behind the scenes, and then this is one of your ranked polymorphic operations. Delta is also is a map adjacent specialization, and then prepend and append you shouldn't have to allocate just for adding an element to the beginning or end of your sequence. So and what is this solution doing? It's once again looking at where values change. So in our example, they're changing from a blue fish to a brown fish or a 1 to a 2. Getting the indices of where those changes take place. That's what where does. Another name for this algorithm is indices, if you're familiar with NumPy. And then by prepending a 0 to the front of those indexes where they change value and appending the size, when you get the deltas of those indices, you're going to have all of the lengths of the runs. So this is kind of would there be a much nicer way of solving this by doing a run length encode that I just realized? Because this is basically a run length encode. Anyways, food for thought. Solve this with a run length encode later on. And then once you have those lengths, it's just taking the minimum of adjacent values, doubling that because you need blue and brown fish, and then you take the maximum of those. So super, super nice. This is one of my favorite examples. A lot of the comments that I showed at the beginning of the talk where people were saying, oh, wow, this looks like Rust, was a reference to this code here because it kind of looks like Rust iterators, if you're familiar with those. And that brings us to our very last example, which is super short. I'm not going to go through this one in detail. And it's a softmax, which is a very famous computation these days because it's used in all of the LLM training. And this is the softmax implementation in Parrot, which is quite nice. So we are basically doing a subtraction, maximum reduction, an exponentiation, and a summation at the end of the day. And replicate is needed in order to get these to work with different shapes because you're basically doing a row-wise maximum and a row-wise sum, and so then you need to use those values with their corresponding rows, so you can use replicate to do that. And the details of this computation aren't necessarily that important. What is important is the next couple slides, which is showing the result of a kernel profiler. That's what KP stands for. And so I have it in the slide deck, but like I said, the benefit of the fact that I'm at a computer right now is I can go to the docs, and if you go back to the home page, you can see that there's a little interactive mini version of this. And if we click the full screen one, it'll bring us to a full screen interactive version of this. And so what's cool about this profile, so if you want to play with this, KP is in the same GitHub repository under the scripts directory. And so KP is just a small wrapper around the NSYS profiling tool that extracts the runtime of all of the kernels on a executable or Python file that you run. So if you build a Parrot executable and then you run this KP tool on it, and also if you have a bunch of other Python files, you just put them in a single directory and it'll go and run each of those codes, strip out the kernel runtimes, and then build this really nice graphic. So, compared to the JAX, TensorFlow, ArrayFire, CuPy, and Thrust examples, and PyTorch, you can see that the Parrot code is the best in this example. Note that this is running on the GPU that I have on my computer, which is a Quadro RTX 8000. It's SM75, so it's a bit of an older GPU. If you run this on newer GPUs, your results are going to differ. I think on the Ampere GPUs, JAX, and I can't remember if PyTorch is the same, but definitely JAX is able to JIT to a single kernel called softmax, which is pretty remarkable. On this one, it's not able to. It gets it down to 4 kernels. So that's what you can see here. The number of colors or if you just look at the number at the top, represents how many unique kernels are being launched by a computation. So the softmax here is basically only launching two different kernels, the row-wise reductions at the end of the day, which is super nice. Versus these other frameworks are unable to optimize that aggressively. Like I said, though, this is on a SM75 GPU, and I believe on the newer ones, JAX is able to JIT down to a single bespoke softmax kernel, which is pretty crazy that it's able to do that. But the point being is you get to write simpler code, and you're generating as few kernels as possible. It's quite nice. And if we go back to the slide deck, I think that brings us to the end. So Parrot, in summary, it's a high-level parallel array-based library with implicit fusion. It is available on the Envy Labs GitHub repo under the name Parrot, Apache 2.0 license. And at this point, I'm happy to answer any questions or collect any feedback if folks have it. Yeah. Thanks for coming to the talk. Is that new? Discord with sound animations of the clapping.
All right. I guess if there's if there's no other question, I'll kind of like go first. There's something I've been thinking about, and okay. Let me start by saying thank you for the talk. Thank you for joining us and sharing. Giving us insight about like what's available with Parrot. So the thing that I had in mind, and I've really been thinking about it, it's actually good that you mentioned the talk that you gave in 2023. I watched the one that you gave at CPP on C. So it's just a slightly different version.
Oh, yeah. There was two different versions I gave, yeah. So
Yeah.
there was the C++ on C talk, yeah. Basically the same talk.
Yeah. So what's stuck with me is something you said at the beginning about the three, almost like the three, shall I say, like generations of, how did you put it?
Yeah, I'll go find the exact slide. Or actually, maybe it's easier to just go to the talk. So this is the one that you watched. It's a bit weird to hear my own voice. And this is the...
Yeah, that's it.
The one that you're talking about. Yeah, and I can't remember exactly how I referred to it, but I said something like, in my mind, there are three different like verticals or camps of algorithms.
Yeah.
Even though technically the last one, if you want to be specific to what the standard calls them, they're range adapters and range factories that are, they show up in the form of views. So they're not quote unquote technically algorithms as the standard specifies them. But, when you've got a transform iterator version, a transform range overload version, and then a transform view version, it's kind of if the first two are algorithms, then the second one surely you can think of as an algorithm at a bare minimum. But anyway, so you're talking about this slide, and what was your question you had?
So something that was coming to me was that in relation to Sean Parent's famous talk of trying to get people to use more algorithms, there probably should be another section to the left of that, which is just raw for loops, kind of like the example you gave in the sushi for two with the many variables and the like. And I feel that many people are stuck in that. It's almost like you're not even part of these three the verticals, as you call them. Like a lot of the developer world is actually to the left, still stuck with kind of like C++. It's kind of like C for loops and index I equals and the like. So I just wanted to get your thoughts about how do we kind of like move people into the, like these three verticals. In fact, even on the other side, there's also like the languages that you talk about. I think I watched a little bit of the video you did. Was it? There are two videos you released this week. I was watching through the first one where the array languages that you just use like a symbol, like a couple of symbols to, represent
Mm-hmm.
array computations and the like. So that's kind of like on the right side. After you kind of like get to know the basics of what transform is and the filter is, and putting them together, then now you kind of like graduate to the functional array based languages and or like Parrot. So I kind of like visualize Parrot being like, after the green to the right. I mean, that's kind of like how I view the vertical. So we have a lot of developers on the left still stuck with for loops, doing things with, like, I mean, like with our industry, to get work, a lot of what people do is like you go into lead code and you just, kind of like figure out which for loop to use. And, like there's very many developers are just stuck in that mindset of like, this is how I get work, go to lead code, kind of like memorize a few ways of solving problems, but that's mostly like the for loop type. So we don't have that. I mean, how do we kind of like move, people across the stack? It's something I attempted to do it last month. I did a talk trying to talk about iterators, and I'm not so sure exactly whether I got through. Kind of like it's what I've been trying to do, trying to bring in it. I mean, people to understand algorithms and know the terms of the algorithms, and kind of like transition to parallel algorithms. Now it's kind of like trying to move the boat along. That's kind of like what the point I'm trying to make. So I just wanted to hear what you think about that take.
Yeah, I mean it's a good question. How do we if and I totally agree that I mean I probably in some sense have become like the bad physics teacher in high school that is very passionate about physics, but he's so far removed from ever struggling with like any of the physics concepts that he's not actually a great teacher because he's so excited about whatever physics teachers teach that like he's got a bunch of students in his class that are just confused and they're just trying to get the basics and like understand and he's just like, oh, like look at this formula and look at that, and he's jumping off desks and showing gravity or whatever, and he's not connecting with the students because the students are like you said, to the left of this thing. They're using for loops. I am definitely guilty of this now. Like if you look, I wonder if do I have the intro? I probably have the intro slide here, except it's not as up to date. So let's go get the one that this is gonna be a long-winded answer. Um, Not that anyone would expect anything less. But and we could actually we could have some fun and go look at like back in these years, 2014, 15, 16. I guess in 2014, 15, I wasn't really even a programmer per se. I was doing programming, but back in 2016 and like 2017 was when I started trying to prepare to get a job somewhere else. I was like 100% for loops. Like let's have some fun. Let's go to my YouTube channel. And this could be very painful for me. Because I never go back. If we go to the look, that is it's hard for me. I used to put like a green screen in the background. It's brutal. It's brutal. But let's just choose like um a random video, and so I don't know what this problem is, but let's just look at the solution. You
Wow.
know? Like one for loop, one while loop, a bunch of locals. I thought I was like, I thought I was, wow, look, I'm making these YouTube videos. How many views does this have? 3,000. And, I thought this is great. I'm sure if we did this for a bunch of YouTube videos all back then, look at this, Domino and trauma node tiling. We're not watching any of this stuff, but it's just like, let's look at the solution. Well, this is dynamic programming. But like, once again, do you see any algorithms here? No.
Nope.
And arguably, some of these, maybe it is the best solution in a coding problem to do this. But at some point, I can't remember. And this is 8 years ago, so this isn't like 2 decades ago. Is that this is how I was doing everything. And then I don't know. I think at some point I watched that Sean Parent talk. So, if we wanted, what is the best advice to get society or at least programmers moving across these verticals? Number one, go watch Sean Parent's talk. I think Sean Parent's, that single talk has basically it's probably responsible for a huge part of my career and the talks that I've given and other talks that other people have given, like the talk that you mentioned that you just gave. So it's number one, go watch Sean's talk. And then number two, tell other people to go watch Sean's talk. And then number three, it's just about, I don't know, at some point I started trying to reach for these algorithms because of that Sean talk. And then I ended up getting some good feedback on these YouTube videos. And so if you skip to later on, I'm still just solving all these, code problems, but then I start covering the algorithms. And once you start to reach for these algorithms, you realize that it's easier to express yourself and solve problems. Like, some people like writing for loops, but in my opinion, I would much rather use some library that other people have spent a lot of time and effort, hardening, and you get these really nice optimizations behind the scene, and then write less code. I want to write less code faster, and then it's just nicer. And then the thing is that it's not just about being able to express yourself better. You get so much stuff for free. It's kind of funny. This is the YouTube video that I just released yesterday, and there's a lot of people that are upset in the chat. We love it, folks. They think they're getting to me. Don't get. I'm winning. When you're arguing in the comment section, my video is doing better. But I guess actually we can go to the live leaderboard. It's basically profiling a bunch of different languages, and if you look at the fastest languages, BQN. In the video, actually, I show that BQN wins across the board, but then someone pointed out that I was only using O2 for the C++ solutions. I wasn't using O3, and the O3 enabled some, I think, SIMD optimizations, and so it's still losing, but it is better than one of the BQN solutions. But what's crazy here is I mentioned that the reason that BQN, the solution for this, is if I go to this, and I just go to BQN here, it's basically you're given a string that looks like something like this, and mob stands for maximum odd binary, and what you want to do is you want to rearrange this string so that it's the representation of a binary number that is odd and is the largest number possible that's odd. And what that means is you want 1 1 to be at the end, and then the rest of the ones to be at the beginning. It's just kind of, without explaining more. And so if you reverse sort, you get all the ones. Just make this a little bit bigger. You get all the ones at the front. And then if you do a 1 rotate, cue the Sean Parent, that's a rotate, that puts 1 1 at the back. And this is if we go back to, where was it? The rankings over here. This is almost as fast if we look at the, I think if I click on this, this is basically the same speed as all of this stuff. And then people in the comments, they're saying, well, you mentioned that BQN, the reason it's so fast is because it's using bit-packed arrays and SIMD accelerated primitives. That's not fair. You have to write a C++ solution or a C solution that does all the same things with bit packing and, SIMD primitives. I don't want to write that code. I don't want to write, to say that, already in order to compete with BQN, this is what I have to write in C++ is a win for BQN. But the point being is this is how I want to express my solutions. If I have to spell it like this, rotate 1 and then reverse of sort of, my argument or whatever, even if I can spell it like this is still really nice, right? Whether it's 5 characters or 15 characters, But the point being is the solution to this problem is very, very simple if you have the right vocabulary. You need a sort, a reverse, and a rotate, or a reverse sort. That's what most languages, they have something that's like some parameter that says reverse equals true or something like that. Um, but like this is how you want to be able to express your code. And if it's faster than everything, it's like I win. I don't have to go to C and C++ and do all this like crazy backflips. And so it's wild to me that people, they're like, oh well, it's not fair. In order to show the true comparison, the comparison is what is easy to write in these languages. What are most people going to go and do? And it's just so the more people that are talking about this stuff and the more videos that are made, I think more people will be convinced. And when it comes to GPUs at the end of the day, which is where I work, like it becomes even more complicated because if you have ever tried to write a kernel for a GPU in CUDA C++, it's very, very painful, like much more painful than having to write some SIMD accelerated thing or C or C++. So if we can provide people a library like this, or even Thrust, because Thrust is still much better than having to hand roll your own kernel. I think it's kind of an argument that speaks for itself. That being said, there's a lot of people that love writing for loops, and guaranteed on every YouTube video I ever make, there's someone like, oh, here's my C solution that's better than, because you don't need to know what a rotate is and what a sort is. And it's like, well, I don't think there's any convincing those people. So, but it's a good observation that you're making though. That like, where I got too many things open now. Where was the talk that I gave? I think I selected away from it. Yeah. This is but this table, it's a good observation that I do really think that most people are over here, and probably as an industry, we should spend more time like focusing on how do you get people from for loops just into this camp. Because now I've skipped past this column, and you're right, I'm over here on the right in like array land with symbols for my algorithms. But what's funny is that people don't realize that I consider like array languages like this, where you're writing with symbols. To me, this is like identical to C++ ranges. This is technically there's no rotate in rangeland, but there is a ranges rotate in C++ 20, and we have a sort in C++ 20 as well. So like this looks weird to people, but like it's just the equivalent of like a sort algorithm. Like these are just succinct ways of spelling algorithms that I show in this talk. And so like probably I've taken it to too much of an extreme where all I have to do is like type some keyboard shortcut. Like these are the keyboards that technically you have memorized in your head, right? Like when I'm typing this stuff, like I type it often enough, but like that's the thing is this is a website that I built. I added a thing where you can just go control space, and if you don't know the name of the symbol, you can just type or if you don't know how to type the symbol, you just type the name, and now you can technically program in these languages now. If I want an iota, it's not there, but if I go to range, and so there are ways to use this stuff, but yeah, I don't know if that answers your question, but it's yeah, we should probably all spend more time. But if you're asking, what's the best way to get people here, watch the Sean talk. Tell other people to watch the Sean talk, and then I don't know, like have little meetups at work if those even happen anymore, because most people work remotely. But like where I fell in love with array languages. If we go back here, my path to array languages was because I was part of a study group when I was at Amazon that was reading some functional programming textbook. And that, before I became a array language fan, Haskell became my favorite language, because Haskell is nicer than C++ in terms of like how hard it is to spell algorithms and whatnot. And so, yeah, I don't know. I'm interested if other people in the chat, if they've got, like you said, you tried to give a talk, and I mean, the nice thing is that I work in research now, so I don't have to worry about convincing teammates to program, because I'm just basically in charge of my own fiefdom. But if you work on a team, yeah, ideally you can convince your teammates to start using more algorithms and stuff, because it's a nicer way to program, in my opinion. But
All right,
in the
thank you.
chat.
And yep, yep, that's a good
Someone
answer.
says, watching. Oh, I remember watching your algorithm videos. And oh yeah, well if you and then they were remarking on the keyboard. So this is BQN, but and this is APL, but there's a language called Tiny APL, which has tried to add every single primitive. So if you look, there's usually, I think, down in the right here, there's, four primitives on a single key. Most of them have one though. Some of them have two, but at most four. If you look at Tiny Apple, some of them have six. Look at this one up here. It's got six on the keyboard. Um, so it's and actually I like Tiny Apple probably the best, because the larger your vocabulary, the less typing you have to do, um, which is nice. So a lot of the times you might be in an array language and they don't have something, but Tiny Apple typically has everything.
Okay. Yeah. So thank you. Thanks for the talk.
Yeah,
But
absolutely.
right. So how much of functional or array programming is memorizing all of these algorithms, their classes, their modifiers, and because you see a problem, you can identify, you can chain these things. I assume it's like maybe lead coding. How in lead coding they say that there are maybe there are different patterns, and once you can pattern match them, you could solve a variety of problems. But this is next level. This is there. I see you composing, like, see this, like this slide. You're composing a lot of algorithms, and when you approach a problem, how do you do this in the first place?
Yeah. Well, to answer your first question, how much of it is memorizing? I mean, memorizing, if you wave your hands a little bit, you can kind of change the word memorizing just to learning. I mean, learning is different than memorizing. Just because you memorize something doesn't mean you totally understand it. But I mean, it is true that you need to learn or memorize, these algorithms. But I think it is worth it. And really, like in C++, there's only like 100 algorithms in the algorithm header. And if you include the views, you maybe get a few more. But a lot of the views are just lazy versions of algorithms that exist, like the transform view. Um, so I like, that is a valid, or is it valid? But it's a criticism that you hear. The people that love for loops, they say, all you need to know for for loops is like, for loops, if statements, and maybe a while loop or something like that, and then you can solve everything. Whereas like for these libraries, I have to go and learn um, all these different things that have different names, and so like where do you begin? Like it's too much. The good news is that it's really not as bad. I only think that there are like, like 100 plus or minus of these things, and really like the fundamental ones, there's only like 10 or 20 of them. And that's kind of why I have this one slide that shows the API overview. Um, is that really like, once you know map, map to, map adjacent, reduce and scan, like you can eliminate everything beneath it, right? Like absolute value, exponential, negate, odd, sine, square, square root. Those are all just specializations of map, right? Um, and so like once you know map, it doesn't matter what unary operation you pass to it. It's the same thing. Um, and the same thing is like map adjacent. Like map adjacent is just a generic algorithm that takes a binary operation that applies that binary operation to adjacent elements. It can show up under a different name with a specialization like deltas and differ, but it's in my head it's the same algorithm at the end of the day. The same thing with reductions. Like a reduce, whether you pass it a plus operation or you pass it a multiplication operation or a maximum or minimum, they're all just reductions. And so really, like, if you wanted, we could take this and we could duplicate the slide, and you could go like this. You could go delete, uh, delete, delete. Technically max by key. We'll leave max by key there because it's slightly different. Delete, delete, delete. These ones I'll keep because, like, and no pun intended. Keep is these are like you do have to think about these a little bit different. Keep is used to implement filter, where, and unique, but they're different enough that you need to learn them. And so when you kind of look at this, it's like, and these are all just like, actually, well, seeing as we're deleting things, we can delete all this stuff too. These are just like front, back. You don't need to learn those. You know what those are. And then so now it's just like, well, we're not actually looking at that much stuff right now. And some of these, I would argue, like, are pretty self-explanatory. Like reverse. Do you need to learn reverse? Not really. Sort. Do you need to learn sort? Not really. And so I guess maybe that would be a good talk. Like, what is the if you're going to start and you want to learn all 100 or 200 at the end of the day, but that just seems like a daunting task. What are like the first 10 algorithms you want to learn? And also too, like, what are the categories? These ones are showing categories based on this API, but there's a couple different ways that you can split up algorithms. On my GitHub, one of my repos, which I haven't updated in 6 years, it looks like, I had this table that I showed in the very first talk I ever gave. And it kind of has, a taxonomy. So how many indices are you looking at a time? Do you have some state, like an accumulator value that you're bringing along with you? Is it a reduction? Are you collapsing things down to a single value, or are you mapping across the operation? And when you do this, you kind of see that all of the algorithms that exist, map into these things. So I agree that there are a lot, but it pays like massive dividends, and maybe I'm giving a talk next month called Algorithms and Combinators, and maybe I will include that because there's a bunch of different ways that you can slice and dice these algorithms, but regardless of the way that you do it, they kind of, a lot of algorithms, like I think, did I had a blog at one point called Algorithm Selection. Oh yeah, look, there's the same table. And yeah, I had this really nice, I made this in PowerPoint, so beautiful. But you can see that all of these are algorithms that exist in STL. But the point of this algorithm is that every single one of these algorithms is basically a specialization of mismatch. Most people don't think of it this way, and most people don't even know of mismatch. Mismatch is probably, oh yeah, I can drop a link to the this cheat sheet. I love how I versioned it 0.0 as if I was ever going to come back and update this thing. And I can also link this this blog that I wrote many years ago. But mismatch, first of all, most people probably don't know about it. And it's terribly named. It's terribly named. But mismatch takes two sequences, applies a binary operation, and then returns the first pair of elements that satisfy that binary operation. So the default binary operation is not equal to, which is why they call it mismatch. You're trying to find where in two sequences do you have a mismatch. But if you take the less powerful version that just looks at a single sequence, and applies it to adjacent elements or a single element, you can get all of these specializations. So equal is the most obvious. If two sequences don't have a mismatch, they're just equal. So you can implement, basically equal as does the pair of iterators that mismatch returns never find anything. And so the point being here is that, once again, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 algorithms of the 111 or whatever the exact number is. As soon as you know mismatch, you technically know all 10 of these. And all of, any of, and none of, like those are three pretty simple algorithms. As soon as you know one of them, I would argue you know the other two as well. So when you look at this at first, it's like, oh, this is a lot to learn. There's so many algorithms, but like, it's actually pretty simple in my opinion. Like I hate it when people say that, oh, it's obvious or it's pretty simple. It's not pretty simple. Like, I mean, you have to spend a lot of time, and to be honest, I spend a lot of my free time thinking about this stuff. But I would say it's not simple, but it's not as difficult or daunting a task as you might think. Um, and and yeah, stay tuned for my talk next month where maybe I talk about these different taxonomies though, and where's the best place to start. Probably the best place to start is with a reduction algorithm, which unfortunately in C++ we've got like 10 different. We've got accumulate, we've got reduce, we've got fold left, we've got fold left first. I think there's a couple others too now. But I mean, the nice thing is at least in C++ we have all these algorithms. Certain languages, they don't have the rich algorithm libraries that we do. So I'd rather be in C++ where it's got this stuff than others. But yeah, I don't know, once again, if I answered the question or not, but hopefully some part of that was helpful.
Thank you. Okay, I'll just ask another one since next is how did you implement the fusion part of the library? Seeing some of these things, or is I'm assuming it's a language feature, like I'm asking from a language feature or library feature perspective, like some of those diffusion, like now in Jax that you said there's a compiler part, there's a JIT part that is actually trying to fuse it, but I'm just curious how yours is doing it without those parts.
Yeah, so it's actually pretty straightforward in Parrot. Like Jax and those Python frameworks, they have the JIT decorator or some kind of decorator. And when you put a decorator on that function, it does something equivalent to basically function tracing, where it's going to build a graph of your computation, and then it does some post hoc analysis of do the nodes in that graph is it possible to fuse them together. So that's like a pretty heavyweight thing. I am doing nothing like that. So I mean, if we just look at a simple, hopefully, let's just look at the single map. This is the implementation of map. It is basically just storing a transform iterator to a sequence, and that's it. I mean, there's a couple extra details because sometimes you can have some, storage that needs to be pointers to that storage need to be passed around, and you've got a shape of your data. But at the end of the day, most of these operations, at least the lazy ones, just map to iterators in thrust, which are lazy. And then if you go to what is a simple algorithm, I mean, we can go to reduce. It's not actually that simple. But if we only look at the first case, you can see that essentially, it's doing different things for the different dimensions. But if you don't specify one, or it's the default, it's just going to reduce all the elements. And so that's just a call to thrust reduce. So it's essentially a library that's entirely built on top of Rust. When you have a lazy operation, you're basically composing iterators with the help of templates behind the scene. And then when you're materializing something, you're just dispatching to an algorithm call. So there's nothing fancy here. It's you know, with the help of templates, we're basically just composing iterators behind the scene, and then when it comes time to launch a kernel, you make a call to an algorithm, and you've got access to both the iterators, and you just make a call to the algorithm. So
Thank you.
I believe we just killed 35 minutes answering questions. I mean, I guess I'm not surprised. You ask a simple question, and then I give another 15-minute talk about the history of my path from for loops to algorithms.
So anyone else? Any other questions? So I think okay. There's something that I was thinking about. I think okay. I wanted to mention this kind of like as an observation, something that I've seen from you and I think Ben Dean, and this has to do with like the the issue of how do you convince somebody to go, how do you convince people who maybe want to are learning programming or are programmers to kind of like transition, to go through the hard part of learning and building up that muscle memory in with the algorithms and the like. And so I just wanted to point out an observation that when you're so excited, when you're so happy, like how, I mean, how you're able to do a podcast to literally talk about algorithms, just, uh, I mean, to speak about them without any visual representation. I think I did listen to this. You do quite a number of episodes, but I caught one where you were interviewing. I believe it was a professor. You were in like a cafeteria or something at a university, and you're speaking with a there's a professor. I can't remember exactly what it was about, but one thing I remember about like listening to that was how excited you were talking about the paradigms. It was something about I can't remember exactly
Oh
what it was,
yeah,
but
it actually might be the one that is just at the front of the page here.
yes,
Maybe, I'm not sure. We were at a pub
yes,
in Cambridge.
yeah,
Aaron, he's got a PhD. I don't think he's technically a prof, although he's definitely taught classes, I'm sure, at some point. And yeah, we were chatting about algorithms, and I was trying to get him to give a compelling argument on why cursity and having the ability to express code with symbols is a pro, not a con. Because a
yeah.
lot of people, they see array code and they're like, well, that's looks like hieroglyphics. Like nobody knows what that means. Like, so that's a terrible idea. But I was trying to get him because he's a lot more articulate and compelling than I am. I was like, "What's your argument for people that say symbols are bad and terse code is it's harmful?"
Yeah, so the point I kind of like picked from that as I was listening to that, and sometimes like when you hear, I mean, even someone like Ben Dean speaking, like he's really excited about little details deep in the standard, like, and you see that comes from that passion, like being excited about what you can actually do. So I mean, even in the videos you just released, see how you're excited about how fast BQN is as opposed to other languages. See that excitement is what would is what I feel is important to creating that interest that would push a typical student, or like, I mean, because it is hard. I mean, to go into all of the nitty gritties, understanding how iterators work, how to compose them together. It does take time to understand, but you kind of like need the analogy is kind of like in my mind is like, like this. You can have a picture at the top of a mountain, the perfect sunset, or perfect sunrise, like something really that looks really beautiful, and you're trying to get people to be like, yes, do mountain climbing, but climbing a mountain is no easy task. But you need to people need to have that that motivation, that like that promise of like, if I press through this, if I go through the hard bit, I mean, there is joy at the top of the mountain, so to speak. So it's an observation of the excitement and the passion that I see coming from, especially you, Bryce, and several other people. When people are excited about what you can actually do with code, then it creates. I feel that that's kind of like the thing to push people to be like, yes, give it a try, and then we can push more people across the three verticals, so to speak. So just as a slight aside of that, I think, I don't know if it was last month or like a couple of months ago, Jensen uh, said something like, this crisis is good for, I mean, the hardware crisis that's going on is kind of like good, like he doesn't mind it. Like, I mean, he makes money from when there's less hardware available. This something he quoted, which was very, I mean, many people are talking about. So the thing I was, the thing that's been coming to my mind is that for a long time we've been having, I think the software industry has been suffering because hardware has been like the ultimate crutch. Just, as long as there's new hardware every year, I mean, why bother learning how to optimize code and write better programs when, I mean, next year the next hardware will just come and, just, I mean, it'll be fast enough. So this crisis could be uh, uh, a wake up. I don't know whether they call it a wake up call, but it could be something to drive better software. I mean, it's challenging us to like, okay, fine, you can't get hardware as easily as you used to. So what? I mean, where do you get? I mean, how do you survive with what you have? So we were kind of like at that point, meaning that I would get better at software, learn, optimize more, think about how you're programming, don't just rush things out the door. Uh, so anyway, just it was the point of what I'm saying is, I noted the excitement, and I think it's an important thing. I mean, to be really excited about what you do and what you can, and that's what would kind of like get more people in the door. So it's just comment on that, and
Yeah, I mean,
yeah.
I totally agree. I totally agree that, I mean, it was Sean's excitement and his C. I guess we should link that video too. We've mentioned it 100 times. C++ seasoning. Um, that yeah, like, it was Sean's. I mean, well, that's the. Uh, I guess this it's kind of sad that the second talk that comes up is one that I made. Um, you guys, I guess I'm not sharing my audio, but folks can. I compiled every time he said rotate. But he's pretty emphatically, you can see the smile on his face. He's like, that's a
That's a
rotate.
rotate, yeah.
And uh, it's hard to describe what is the equivalent of the sunset and the beautiful view that you see at the top of the mountain. Like, what is the equivalent of that for like the algorithm journey? Uh, I don't know. I mean, I think honestly it's great, and like there is a sunset. What exactly the equivalent of it is, I'm not sure. But I'd also say that like a part of hiking, if you want to keep up that analogy, is that like the hike itself is also beautiful. Like if
Yep.
you've like it's not necessarily just about the sunset at the top. Every single step of my journey from for loops to Haskell to, or it was for loops to C++ algorithms and lambdas to Haskell to array languages, to array languages and GPU computing. Um, I don't know. Maybe everyone's wired differently, right? But like I love discovering new ways and like patterns and idioms and algorithms to solve problems. Like um, I just absolutely like love like the parrot, not the parrot, the sushi for two problem, that is somewhere here. I mean, I gave this a version of this example at a Q conference of all places in New York. And someone came up afterwards and said, "Oh, like, do you know that you could solve this a different way?" Which was the computing the indices and getting the lengths. And I had never thought about it. I was solving it an alternative way before. And when he told me that, I was like, "Oh my, that's amazing. Why didn't I?" And the thing is it's a simple toy problem, but the idiom, the pattern of computing indices where values change so that you can then get the length or the difference between where those indices are, that's a way of computing the length of segments without materializing like a nested list of segments. So it's a lot more efficient. And so it's a simple toy problem that I've talked about at a couple different conferences. But then, I give it at this one conference, and then some guy comes up to me and he's like, "Hey, you know that you can do this like a much better way using this other kind of pattern." And like that's the best. Like that is, it doesn't happen every Sunday, every Saturday or whatever. But if you're going around to these kinds of meetups and talks and conferences, inevitably you're gonna run into people that are telling you this stuff, and it's fantastic when you're able to put like that kind of pattern or idiom or tool in your like algorithm tool belt. And yeah, I think it was Uzo mentioned earlier. It is a lot of work. It's not something that's going to happen overnight that these algorithms. It's like a lifelong journey, and like it's not. I don't actually think there's necessarily like, oh, if you spend a year doing this, you're gonna hit this point, and then everything's gonna be amazing. I think you start today, you learn one algorithm, and then 5 years later or 8 years later, in my case, you know, you've learned so much, and the way that you can solve problems in your day job is just like infinitely better than when all I had was for loops, while loops, and if statements. So yeah, I totally agree, and that's why you got to go watch Sean's talk, because he's the guy that started it all. I mean, technically, Alexander Stepanov started it all, because there's another great talk if you want to generic programming. Do you think it's going to bring up Sean's talk? It does not. You're gonna have to put Sean Parent. This is one of my favorite talks. He gave it at Pacific C++, and there's a specific point in the talk where he's talking about Alex Stepanov and the implementation of. I probably got to watch this talk again, to be honest. Yeah, because it's been a few years since I've watched. Yeah, I don't exactly know where it happens in the talk, but anyways, it's a fantastic talk. And in this talk, Sean is talking about how Alexander Stepanov inspired him. And so it's just a bunch of people out there inspiring each other. I was inspired by Sean. I inspired a couple other people. Sean was inspired by Alex. Alex was inspired by 2,000-year dead mathematicians. And yeah. So the more we talk about this stuff, I think the more people will go from the for loops to algorithms.
Yep, I agree. I hadn't seen this talk, so it's something I'm going to make sure to have a look at. So thanks for that.
Yeah, maybe I'll tweet it out. I'll say, for those of you that haven't seen this amazing talk,
Yep.
reminder, you should go watch it. And like I probably got to watch it again too, because I probably watched this as soon as it came out, because I started watching talks back in like 2017, and in fact, actually, well, I don't want to bring up the spreadsheet on. Actually, maybe I can. If I go to this and I go to videos, I have a spreadsheet that tracks, except I lost the first, what is this, 47 talks. At some point, I just accidentally hit the delete key. And I don't know. I will never know now what the first 47 talks I watched were. But I keep track of every single talk that I've ever seen. So the most recently I watched David Senkel's Rediscover Software Engineering, but I've seen 1,537 talks since I started watching talks. And if we search for generic programming, so yeah, I watched it on November 13th. When did it come out? It came out on October 23rd. Well, I was hoping it came out like literally the day before, but clearly, I waited 2 weeks, or it wasn't on my radar until then. Um, but yeah, it's been, and I probably haven't. A lot of talks that have generic programming in the title. Yeah, but so I've only seen it once. So it's been, what is it? It's 2026. Man, that makes you feel old. Um, so 8 years ago was when I last watched it. So gotta watch it again. All right, is that it?
Yeah, I guess we could give the floor to anybody who has any thoughts. Anyone? Or just say hi, you know, comments, compliments, and the like.
Is this recorded? Is this gonna go on YouTube or
Yeah,
not today?
I usually try to record it. I hope it's recording. I believe it is, but I missed the first maybe 20 minutes or so due to a network issue. But we usually try to record and put it up on YouTube. So we actually have, I think 5 or 6 talks up on YouTube for the last meetups. I'm not sure the number, but we actually, I mean, we usually just throw them on YouTube because there are people who are part of the who are part of this group, but they're not able to make it. So we just want to make sure to, get whatever knowledge we're sharing out to as many people as possible.
Sounds good.
All right, so guys, you have the floor. Paulie, Jean-Philippe, Dennis, Emmanuel.
All right. Yeah, thank you very much, Kona, for honoring our invitation. So, was that last week? Yeah, so I was having a conversation with Mike Shah. So I told him about the meetup, and you'll be the one who will give a talk. He was like, "Oh, Kona is a very good speaker." I was like, "Oh,
That's nice
cool,
of him
cool,
to
cool."
say.
Yeah, so and I was so excited, and here we are today. You did a very good job.
Thanks. I appreciate that. All right. Well,
I just want to say something. I'm just wondering how much I would be able to quickly pull them up during a lead code problem and not be debugging the because my problem with iterators and the ranges libraries and everything is sometimes you might compose them in a way that the debugging session makes you like it gets longer than if you started thinking about it from a direct program like way from using for loops and ifs. Especially, I would say this happens mostly in string and all those yeah, or anything that deals with array array values in a container. So and so anyways, so I've known your Parrot library for a while and it's really good. So one of the features, so that'll make me point out the feature that you mentioned about printing the intermediate steps. So I think that would be very useful for especially in that particular situation, just while learning.
yeah, I've definitely found it useful. And the nice thing is that typically when I'm programming, in Parrot, I'll have something called, like array equals whatever, dot dot dot. But then you can start chaining things like this, and then I'll just have a print statement here, and then so like I'll compile this and evaluate it, but then next time I'll do some whatever other operation, and so each time you can just compile it, and it kind of then works like a REPL, right? You're just incrementally building up the solution you want. And you can do this with ranges, but you just have to do like std print ln And then I don't actually, there's some kind of syntax where you can do it like that, but it doesn't work as nicely in my opinion because like the range formatting only is supported to a certain extent. Like if you have a range of ranges, I can't exactly remember it. If you use the format library, it's better, but then you have another third-party dependency. So yeah, the print thing is I basically added it for my own self, but then it ended up being like a super useful thing just for debugging and whatnot. So, all right, well, we're at the 2 hour mark, so I guess I should say thanks to all of you guys for coming and asking questions and um, yeah, the discussion afterwards. This has been fun.
All right. Thank you so much.
Thank you.
So enjoy
Thank
the rest
you.
of your weekend.
Okay, you too.
Bye.
Thank you.
Uzo, how you doing? Matthew, how you doing?
I'm okay. Hello.
Yes, hello everyone.
Hello, everyone here.
You
So,
know, the
I,
talk was like it was a bit strange and technical because I've not really had an experience with working with Parrot Library. So I was just paying close attention, taking notes, and then looking at some of the resources. Yeah, hopefully very soon I'll jump into the wagon.
Okay, I would say that to be honest, I've not used Parrot in any project. Well, I think they make it similar enough to the ranges, as you see, they draw parallels with the ranges, the standard algorithms libraries, and the others, because it's all of them fall in the same class of, as I said, functional and array programming. So I so I think that's the goal, but then taking it to another level, and hopefully not to the level that we're using Unicode characters that are very, I don't know how to type them with its keyboard. The APL and BQN level of parallel programming.
So when I saw that demo he did, I was like, "What's this? Is he writing in an alien language?" Uh,
Yeah, that was that part caught me off guard. I was really surprised.
yeah, so it's actually quite interesting. Yeah, even I tried watching the video. I mean, the example actually that he gave, I just watched that bit and I was like, okay, fine. I left it at that. I was going to continue watching it later. But what I'll say is there's this idea that I think it's kind of like getting lost, especially when it comes to the C++ library. You see that the last vertical that he talked about, um, ranges and the views. So one thing that I'll say about the algorithms in general is that the when you try to program with just the algorithms, there there's this notion of like you have to do like a pass, that you have to do another pass and another pass, because each algorithm is like its own for loop, and but it does a specific thing. So the old way of programming is that okay, when you do like multi-pass separate times, so then now there's ranges where it's the same thing. You're just doing multi-pass because each algorithm is start to finish. So if you're adding, you do a reduce, then you take that and you maybe pass it to another algorithm and that kind of thing. So the thing that really changes is the range based views, where now you're not just going through, but you're kind of like setting up work to be done later. So it's like, I mean, that joining of work to be done, then it takes a certain chunk whatever collection that you're working with, and it goes down a certain pipeline. That's kind of like the paradigm shift. Then now add that now to this BQN, and it works like the views, but instead of typing like say rotate, you just put a one, just a symbol. I mean, it looks very weird, even when you see like when you watch his if you go to his YouTube channel and watch the latest kind of like range of videos, you'll see just a few glyphs, and he's like, okay, here's a program, and it's like three things. But if you know, okay, fine, that first one's a rotate, then it's like a scan, and like the other algorithm. So you kind of like need to start with the normal algorithms and see how they operate sequentially. Then you kind of like transition to being like, okay, fine, if this is how it works sequentially, how do I the point is this versus this, so to speak. So it's like a step in the journey. It's like somewhere you get to after some time. It's that's how I view it. I don't know if that makes sense.
Yeah, it does. Because especially, I think ranges changed a lot of things. Because one issue I had was when I used algorithms, it would you might end up maybe needing to do something slightly different from what the algorithm performed, and you wouldn't want to do those multiple passes. But with ranges, you could just get views out and then do those things easily. So it ends up being even more efficient, at least. And also, I think, okay, let me think. Okay, and also for especially the lazy part of it, that it's only materialized when you need it at that point. So so yeah. And but my fear as well, because people always complain that if your code isn't simple to understand. But I guess the argument is when everything is more of standardized in the form of categorical thinking, that there's this is a rotate, as he referenced in one of the videos, or this is run length encoding or something like that, like he mentioned regularly. The code ends up being still simple. So it's that argument where when they say make your code simple to read, but then the question is simple is subjective. So, but we are in the programming business or programming uh, work, and these are expectations of people that think in terms of algorithms or think in terms of functions and arrays. So, I guess at the end of the day, it's still simple, it's still readable, it's even more terse, and it's so I don't know the former detractors of algorithms and iterated and ranges and the rest. I don't think it holds now that I've been now that my eyes have seen and my eyes have been open. So yeah, it ends up being terse. We've seen it countlessly. Just trying to map out what the for loops and ifs are doing, you would get confused. Except you follow it line by line or you comment out heavily. But once you see those rotates, you see those things, it just makes sense. Yeah, that's what happens.
Yeah. So I wanted to just add and say yes, they especially in the C++ views, they are they are hard to debug, but in essence, you see the debugger is really not the tool that you're supposed to be using when trying to diagnose. Um, I mean, you kind of like need to be more like relying on tests. So you write tests, then I mean, so if you tests, the thing for using the small unit tests and the like. So it's like the debugger really shouldn't be the tool that you reach for. It's I mean, it's kind of like lifting up to another level where you just you rely on the tests that you've written to kind of like figure out what's going on. Especially now, once you get that muscle memory and you start seeing how things compose, then especially with larger like data sets and the like, then it becomes faster and easier. The only thing, the challenge, or rather at the moment, is that for example, the range-based algorithms are not parallel. So writing parallel lazy iterated collections is kind of like it's like a new area. There are a few talks. I think I saw a couple of talks of like how it needs to be done. But what happens is it's all about chunking, uh, ch- like chunking up the input and then now running that to whatever it is that you need. That's what there's a talk I think by Bryce. I've linked it a couple of times, but that's the essence of it. I keep on saying that it took me a while to get it because this idea of chunking. So if you have like a really large data set, then you chunk it, then you split the work. So it's kind of like what happens with the lazy view. Just that instead of the lazy view, you go one by one, but you do like a whole pipeline for each block, but I mean each element. But now with the how it works is that to have parallel algorithms on a big data set, you have to split it. You create like smaller chunks, and then now you pass those through whatever pipeline you have. So it's something to look into. It takes practice. There's no shortcut. I mean, to even like really understand what happens with iterators, it takes some time to kind of like get that mental picture. But once you do, then it's like you just see. I mean, you literally see how. Um, I mean, you saw like what he was using, just a few symbols. You're like, yeah, I'm going to rotate and scan and print, and you just compose and you just work on that level, which is a lot faster. You don't even think debugger. You just it's like I expect maybe this amount of data to produce this. So the point is the tests are what kind of like you use as opposed to the debugger. If you try to debug, it's really hard. I mean, it's pointless basically trying to read through all of the template initial. I mean, it's terrible. Yep.
Yep, I agree.
Yeah, sorry, we can't hear you, Uzo.
Oh no, I'm not
Yeah.
saying anything. I was just providing feedback, Mr. Martin.
Yeah, so I'll
But
just
okay.
shout out to Jean Philippe and Dennis. I hope you're well today. I'm sorry. Maybe just repeat that. I don't think I got that. It's breaking up a little on my end. I don't know if others can hear.
Oh my God, sorry for that.
Yep.
One, two, three. Oh,
Hello.
ah, yeah, I'll be trying to meet. Yeah, I'm going. What was kindly them? But I
I don't know if anybody. I was having trouble hearing what you're saying. It's coming on and off. I don't know if everybody else. Maybe problem is on my end. Can you hear me?
It was the same on my.
Oh, okay, fine. Then I guess there may be a network issue. We couldn't hear John Philippe.
now.
Yeah.
Okay. Yeah, I was actually saying that it's time to achieve it and work. Yeah, I think probably it takes time to think more about it and see not so improving time to try.
So I think there seems to be an issue with the audio. It comes on like for like a second and then goes off. Then so I'm not sure whether we're
Yeah,
catching. I'm
I've
not sure
been
whether we're
dealing with this.
catching.
Sorry for that.
No worries. So anyway, I'll just say thank you for coming. I'm sorry that we're not able to catch what John Philippe was saying, but you could always just put it in the chat. I'm sure. I know you've been doing a bit of work with GPUs and especially like of late in your library. So I'm happy that we got like a good quorum. We're able to listen to Conor, and I'm sure we learned a lot, or I have been inspired to kind of like climb the mountain, because of course like where he is we want to get to that point where we can just put a few symbols and say that's my program. So I just want to say thank you all for coming. Thank you, Dennis, Uzo, and Jean Philippe. I'm thinking we may need to close it there for today, and we'll always can always get in touch with each other and the like. So I'm thinking it's good to close there, unless there's something else anybody else wants to say. Okay.
That's fine. Thank you, everyone.
Okay. Thank you.
Okay. Yeah, thank you. Thank you, everyone.
Okay.
Okay. Bye.